All right, so basically what we're going to do is, this is stuff that you guys should already know, but we need to learn it in depth. We really need to know functions and parent functions. And so we spend a lot of time, in Algebra 1 you learn basically linear and quadratic equations or functions, and you learn their shapes, you learn what they look like, you learn how to determine things. And now we're going to learn 12 basic functions. So the first function is the identity function. It is f of x is equal to x. All right. Now what is the domain of this function? All real numbers. What is the range of this function? All real numbers. Does anybody want to take a guess as to why? And you should be writing these down. Draw this graph in your notes. I know you look at it and you say, well, I know that f of x equals x is the diagonal line. But why do they call the identity function? They call it the identity function because when x equals 1, what does y equal? When x equals 2, what does y equal? Get it? It's the identity function. This is the only function that acts on every real number by leaving it alone. Some functions are bounded, so they don't necessarily cover all real numbers in the x and y direction. This one literally covers every single number you could think of by itself in the x and y direction, from negative infinity to positive infinity, both in the x directions and the y directions. Can I move on to the next graph? Okay. Next is, we call this the squaring function, but it's really x squared. So this is f of x, x squared. It's bounded from below at y equals 0, so the range is 0 to infinity, but the domain is all real numbers. It's a parabola. So let me just read the interesting fact. The graph of this function is called a parabola, and it has a reflection property that is useful in making flashlights and satellite dishes. So the satellite dishes or a flashlight well, I'm a physics teacher. You can make a lens and focus the light in a certain way using a parabola. Okay? And satellite dish signals are electromagnetic radiation, which is like light. So the same properties that apply to a flashlight would apply to a satellite dish. That's why satellite dishes are always curved, because it focuses in on, and it'll focus in on that one point, the focal point. Okay. Next is the cubing function. It's f of x is x cubed. Interesting fact about this parent function, it is the origin is the point of inflection for this curve, because the graph changes curvature at that point. We'll talk a lot about point of inflections when you take calculus next year. But basically it has to do with a function increasing or decreasing in the concavity of the function, or the curvature. Prior to the origin, it's curving clockwise. After the origin, it is curving counterclockwise. The point of inflection is when that change occurs, and that has to do with concavity. So in the real world, what we try to do is, if we see a parabolic data, we would try to fit it to some sort of squaring function. If we saw linear data, we would try to fit it towards some sort of identity function. But it's not really, we would no longer, we call it a linear function, but it's no longer identity function once we start to transform it. And then a cubing function, if we have some sort of behavior that looks like this, we can manipulate some variation of x cubed to get it to fit the data. Next we have the reciprocal function, or 1 over x. You guys should know this. In our previous section we did a ton of problems that had vertical asymptotes that occurred when x, or the denominator, equals 0. So sometimes certain values of x will cause the denominator to equal 0, and you will get a vertical asymptote, and you would get this kind of swoosh swoosh look, right? That's what I call it. But here's an interesting fact about the reciprocal function. This curve is called a hyperbola. Not a hyperbole. Hyperbola is how some people say it, but a hyperbola. And it has a reflection property that is also used in some satellite dishes. So it kind of has like a focal point as well. So if I look at data that looks similar to this, I can fit it to some sort of reciprocal function or a transformation. I might stretch it, I might shift it left or right, I might shift it up or down, but I could try to fit this to my data. Next we have a square root function. F of x is equal to the square root of x. Here's an interesting fact about this one. You can put any positive number into your calculator and take the square root, then take the square root again, then take the square root again, and so on and so on and so on, and eventually you will get 1. Why don't you go below 1? Well, you could, but if when you get, what? No, what's the square root of 1? 1. The square root of positive 1 is 1. So at some point in time, once you get down to 1, that's it. Now, truthfully, they're fibbing a little bit here. It's true if you did that with your calculator, but you have to round down, round down, round down, round down, and eventually you'll get 1. No, wait, let me take that back. No, because the decimal would get smaller and smaller and smaller, and eventually you would end up at 1. Yeah, that's true. All right, this is the exponential function. Now, this is based on the number e. It's Euler's number. It's like pi. It's an irrational number. It shows up in a variety of applications. The symbols e and pi are brought into popular use by Leonhard Euler. Well, pi's been around since Archimedes, but Euler liked to use irrational numbers. And so e actually represents him. It's about 2.72, I think. Or 2.71, I can't remember off the top of my head, which is funny. That's the one I should know. Anyways, if you were to graph f of x equals e to the x, it looks like this. And so sometimes, and this is great for like exponential growth, like population models, right? We also have the natural log function, ln of x. And this function increases very slowly if the x and y axis are both scaled with unit lengths of 1 inch. You would have to travel more than 2.5 miles along the curve to get a foot above the x-axis. So it's a very slow growing function. By the way, the exponential function and the natural log are inverse operations of one another, which means they reflect across the identity function. So see how that swoops that way, and this swoops this way. See? They reflect across the identity function diagonal. Okay? Sine function is a trigonometric function. This function and the sinus cavities in your head derive their names from the common root, the Latin word for bay, This is due to the 12th century mistake made by Robert of Chester, who translated the word incorrectly from an Arabic manuscript. Ironically, though, we call it a sinusogenous function. It's an oscillating function based on the unit circle. This is symmetrical about the origin, so this is an odd function. Why are you giggling at that? I don't get it. Oh yeah, Bay is used differently now, isn't it? She's just like, I can't believe he said Bay. Cosine function is an even function. It's really just, if you were to take the sine function and slide it over a little bit to the left, you would get the cosine function. In fact, cosine and sine are called co-functions. That's where we get cosine from. Cosine is the co-function of sine, and we'll talk about that in chapter 4. But the local extreme of cosine functions occur at the zeros of the sine function and vice versa. So, see where this crosses the zero? Whoops. On my sine function, that's the peak. So here, right here is a 0, but on the sine function, it's a local maximum. That's what they're saying. Sometimes we use a cosine function to fit a little better because of the way that the function starts. It starts at 1 when x equals 0. Now an absolute function, an absolute value function, or as we enter it in the calculator, ABS parentheses x, it has an abrupt change of direction at the corner. We call that a cusp. That occurs at the origin while all other functions are smooth. We'll talk a lot about that in calculus. Next is the greatest integer function. We call it the greatest integer function. And this function has a jump discontinuity at every integer. We also call it a step function because it looks like steps. Don't leave yet, we're almost done. This is called a logistics function, and this is what it's graphed like. We use this in the real world to model population growth in biology, and it's used for all kinds of ecological systems and modeling and stuff. And then that's it. Home.